Alright, so this is our introduction on truss analysis for the HSC Engineering Studies course. You would have previously seen bridges in real life, and bridges are made out of real materials. And because they're real materials, they can handle forces in all directions to some extent. If you have a metal rod, it can handle forces in all directions. It can even handle torsional forces like twisting. But if we look at this question over here, this HSC question, this is from the 2020 HSC exam, question 25. We see over here a simplified version of a truss. So, or this over here is a simplified version of a bridge. If we, and it's also like a 2D version. And over here they are simplifying elements of this bridge to enable us to calculate it. Just like in physics, you might do experiments where you remove wind resistance or friction. We do the same thing in order to do truss analysis. So we're going to start by explaining what is a truss. A truss is a simplified version of a structure. For a simple way, let's just say that it's a version of a bridge. And a truss involves three major areas. We have our joints, we have our nodes, so we have our joints, we have our members, and we have our reactions. And if you're looking at other information online or a textbook, they may also use a different word for joints. They may also use the word nodes. So we have joints, we have members, and we have nodes. And let me just fix up the focusing on this camera. Right, that should be better. So let's show what an example is. Let's say we have a very simple, we're just going to have a bridge that spans, right, this over here is like a valley, and we have a very simple triangle bridge here that we can have if you've seen anybody play poly bridge, right, they're going to have their little truck over here crossing the bridge, and that's all fine. This over here is a real world scenario, but we have to simplify this before we can start to calculate the maths. So if we look at this, we can simplify that this is just going to be a triangle, and we can look at the structure to determine how we can break it down into these three elements over here. Firstly, we have the joint or the node, so that is anywhere where we have two pieces connecting together. So if we look over here, we have this location over here, this location over here, and this location over here. This is where two members are connecting together. And then, I should have explained it in the other way around, but these over here are members. So if we name these, let's call this is member A, this is member B, and this is member C. We can see anywhere where there is two or more members connecting together, we call that a joint or a node. Then the last part we have is this over here is just going to fall to the ground if nothing else is happening. So we need to have some form of a reaction. So if, we denote this by triangles or some sort of icon to show that it's connected to the ground. So we're saying this over here, this is where this is connected to the outside of the scenario or whatever we're picking. The last thing we have that is missing from here is we're going to put a load into the system, but we'll deal with that later. So that's the simplification of what we have for a truss. Now there are some rules that we have here because we have simplified a real structure, and we just got to understand what our simplifications are. When we talk about our members, we have to say what a member is. So a member is think of it like a piece of metal or string or something that is very long and thin. All right, so we're talking about like a mathematical line. Right? It itself has no thickness because we're trying to simplify it. It is long. That's long compared to its thickness. So if you look at a bridge in the real world, if you see any piece of the metal or string or whatever, if you would think of it as a long, thin, if it's longer than it is thicker, you could assume that that is a member. Members also can only, what's the word I'm looking for? They can only translate force in the direction of the member. Let me just show what I mean by that. So if I do a 3D, so this over here is a member. It is clearly a long and thin member over here. It can only translate force in that direction, right, or that direction. It can only go in or out. It cannot translate any force in this direction or that way. It also can't transfer a moment. And it can't twist around itself either. So it can't do any of these. It can only do forces in and out. You may already know some terms related to this. We call it tension and compression. Right, so it can only do forces in that way. This is the main thing we use to simplify our bridge. Because if we have our bridge over here, if we can now know that in our bridge that no matter what's happening with this structure, this member over here can only translate force in this direction, and this bottom piece can only translate force in this direction, and this can only do force in that direction. So we can start using these simplifications that we've made to help us solve these mathematically. If we're talking about in the real world where they can translate forces in all these directions, we have too many unknowns for us to successfully solve these questions. Right, so that is members. Our next part we have is our nodes. So what is the rule for our nodes? And this is going to put me onto a new page, or not. Right, so then we're going on to what is a node. So a joint. So we already have the rule that a joint connects two or more nodes. So a joint connects two or more members. A joint is, if you think of a member as like a road, a joint is like the intersection between multiple roads. And if you want to think of a force traveling through a bridge or through a structure is like cars traveling through a road. If they want to get onto another road, they have to go through an intersection. And just like an intersection, the amount of cars going in one direction has to equal the amount of cars going out in the other direction. So all the force must go through the joints. The last dot point we have here is we have over here, we have the example of these are the supports, and the supports is going to have the reaction forces. And if we look at the example we have on the HSC question over there, where we have A and B are our supports, and they're going to be providing a reaction force. But we also have, starting from left to right, we have the 1.2 kilonewton force going down, we have the 20 kilonewton force going down, and we have the 3 kilonewton force, which is like on the top right section, and it's going to the left. These are external forces, so they could be, in this example, they could be cars. The top one could be an example of like wind. These are forces that they're experiencing. And when we get our truss analysis, we have to put our external forces into our question somehow. Otherwise, we're going to be solving well, as my maths teacher would have said, a trivial solution where everything is equal to 0. So when we are putting in our external forces, we have to put those forces on a joint or on a node. So external forces have to enter the scenario on a joint or a node, which makes sense in a way because you can't put a external force on a member because a member can only handle force in this direction. So if your external force is anything other than exactly the right angle for this member, it's not going to be able to transfer that force to the rest of the structure, and it just won't work. If there's any form of I think it's transverse, I think is the word, but I'm not exactly sure with that. If there's any sort of force in like this direction, your equations won't work. It's like it'd be equivalent to trying to divide 0. So all external forces has to happen on the joints. Then the next thing we have reaction forces, which I'm going to go over to this lovely paper over here to start talking about our reaction forces. So we have supports, is how we connect our bridge or our truss to the real world. We use the word supports is just to define how it's connected to the real world, and the supports are going to be providing the reaction forces. The reason why we use these words in these diagrams is the different types of support you have determines what reaction forces you are introducing. Starting from here at the top, we have the simplest supports, and these are called rolling supports because they have a little triangle with little wheels. So you can think of these little wheels as like rollerblades. Right? If you have a person on rollerblades, they're very easy to push over, or they're very easy to push in a direction, and they can slide. Or same with like an ice skating, they can go in one direction very easily, but typically they don't fall through the ground because the rollerblades are giving you support that you're not falling through the concrete. Same thing over here with this bridge. In this first example over here, in this first support example over here, actually this way is better. Right, this over here is a triangle with the rollerblades over here. This support is able to move left and right very easily, but it is going to be providing a force onto the structure vertical. So that's why this particular rolling support over here provides a reaction forces in the vertical. And as we actually see this over here, this is the same one that we have in our HSC question at point A. Rolling supports can happen in multiple directions. You can actually have a rolling support here. This is a vertical rolling support where it can move up and down easily, but it's providing support in the left and right. So this is the reaction forces that can put on our truss. We can, in theory, have it at any angle. We can have our rolling support. Is a 45-degree one. The rolling support provides a reaction force perpendicular to whatever the direction of rolling is. Then we have our next level of complexity, which is our pin joint. So when we consider a pin joint, it's like you have our support, and then you know how you have those metal rulers that have the hole in them? So if you think of like if you were to get a piece of wood and then you were getting a nail and you nailed in that hole on the metal ruler, you're still able to rotate the metal ruler in all directions. But if you put any translational force on it, like up, down, left or right, it won't move. That is what these pin joints are doing. So the first, these are all examples of pin joints. This one over here looks a lot like our point B in our HSC example, but it can be in all directions. Sometimes they can be graphically drawn like this, or like this. The key thing to look for, if you see any of these lines, right, that means it's like connected to the surface. So that's a dead giveaway that this is a pin joint. It's not moving. And pin joints can provide force in the vertical and horizontal. They actually provide forces in all of the X and Y directions, so any angle. But it's going to help us in our calculations in the future if we say vertical and horizontal, so we can break down our when we're going to be breaking down our questions into vertical and horizontal components. If we already consider that our pin joints can work in both vertical and horizontal, that's going to make that a bit easier. And the last form of support is a fixed support. So this is interesting because this is what all supports are in the real world, because we don't really have like loose pins in our bridges. We have things that are like welded together or riveted together. But when we're solving truss analysis, we can still use fixed supports in our examples. So think of a fixed support like you have, do we have a flagpole at our school somewhere? I think we do. But let's say you have a flagpole and it's just like wedged into the ground, right, nailed into the ground. That flagpole is able to provide force in the vertical and horizontal, but it's also going to stop rotation. Or think of you have a pole into the side of a building. Right, so let's say, how's this paper? Say you have a building over here with windows, whatever, and let's say you have a flagpole coming out like this, right? And so it's got like a flag over there, and it's coming out of the building like that. You may have seen things like this before. This particular thing doesn't have any support on this side, so this is going to have to be welded in or something like that. So this over here has to be able to withstand a vertical force and a horizontal force, but it also has to be able to withstand a moment. And this is the most complicated example, and I'll show you one of those in the future, but I don't usually see it as a HSC question. If anything, I see it as a multiple choice question for the most part. So that is our supports, and the last part we have, this was not part of the 3 dot points because this is something that's going to be introduced by the question. We'll have this, and the previous 3 things we've had members, we've had joints or nodes, and reaction forces. These are our 3 things that we solve, so they're like considered our unknowns in our scenario. The things that are known, we usually know our distances, like we know the geometry of the situation, but we also know our loads, and like in our HSC example over there, 1.2 kilonewtons, 20 kilonewtons, and 3 kilonewtons are our loads. But our loads, again, we're simplifying it, so we have to understand what our simplification of our loads mean. All our loads in our simplified example are point loads, which means they act on that single point. Our load is a force, which means it's a vector, which means it has a magnitude and a direction. For example, 20 kilonewtons going down. That's exactly like our HSC example. And as we described previously, it has to act on a node or a joint. It can't happen. So this example over here can't happen. I just drew it for whatever reasons. The other forms of loads we get in not so much our truss analysis, but in our when we do bending moments in another topic. But they can demonstrate the question in the form of this. We could get distributed loads, which look like this, which is a load that happens over a distance. So this could be like the Harbour Bridge might have multiple different cars. It is a force and a distance. So over here we have 10 kilonewtons per meter, which means this, if we go 2 meters, we can find out the total force because it's 10 kilonewtons per meter times 2 meters equals 20 kilonewtons. They also have a direction and a length and a location. So when we want to, if they give us this form of load, we can still simulate it by converting it into a point load, we calculate that it's 20 kilonewtons, and we get the average distance. So this is 2 meters long, the average distance is 1 meter in, so that's why this example we go down by 1 meter. The other form of load we get is a rotation or a moment load. So like the example of an aeroplane has like a motor spinning, the propeller's spinning. They have a magnitude, they're in Newton meters, they have a direction which is clockwise or counterclockwise, and they have a location. And we can still simulate this load, has to be entered into the system on a joint or a node. And we can solve this, and it looks like our rotation. So that's all it for our introduction into truss analysis by just understanding what the key terms are.